Now let's proceed towards the more of the medium specific speed regimes, and let's look at the next example, which is the corner separation in vane diffusers. And again, you can find more detailed information on this from this paper, which was published in ASME Journal of Fluids Engineering. So vane bowl diffusers are typically used in centrifugal and mixed flow applications. So as you can see here, you have the impeller, and you have the diffuser to turn the flow essentially from an almost radial to an almost axial direction at the exit of this vane bowl diffuser. So it's really quite a complex three-dimensional diffuser, and what we have seen in these vane bowl diffusers is you can actually have quite a strong corner separation, and these are actually CFD predictions, and this is the corresponding oil flow visualization for this diffuser. And what you can see is that the oil flow actually confirms this strong corner separation, what we saw in CFD. Also, what you can see in the CFD is that as a result of the separation, you get a very non-uniform flow at the exit of the diffuser. And again, this has quite a major effect on the performance of the stage. So their aim was to try and see how one can reduce this exit flow non-uniformity. And then what they did is to use this detailed CFD of the baseline conventional stage to try and understand what is actually happening. And as we saw, it's a very complex three-dimensional flow analysis, and you really need to think very carefully about what's coming out of your CFD. What I'm showing here then is three different sets of results. So first of all, what's interesting is that at the region where the separation is happening, you can clearly see the location of the separation from these CFD results. And you can see that this corresponds to this region of high positive pressure gradient at the hub. And this is actually happening where the meridional shape has sort of a bend here at the hub. Now, although there is a correspondence, but positive pressure gradient alone does not actually result in a big corner separation. It could result in a simple separation bubble, but not this sort of a tornado type separation that we are observing here. So there must be something else happening, and so the stagnation pressure contours were plotted, which we see here at the bottom of the slide, just before the separation. And what's interesting is that in this corner, inside this blue dashed line, you can actually see quite a strong accumulation of low momentum fluid at this hub suction surface corner. And in fact, what's really happening is that when this low momentum fluid hits this strong positive pressure gradient here, then you get this huge corner separation that we are observing here in this diffuser. So the question then is whether there is a way we can eliminate this separation at all. So in fact, what they finally came up with is this kind of loading distribution, where we have a Fore-loaded distribution at the hub, and we have a mid to aft loaded distribution at the shroud. And really the way the Fore-loading works is that it diffuses the flow very rapidly at the hub, and it also removes the region of that high positive pressure gradient. So if we go back to this diagram, then this region of high positive pressure gradient is actually moved forward, and so this could be a good thing. But that on its own doesn't help, and we still get a separation, and hence the importance of the aft loading at the shroud, because then we end up creating quite a strong secondary flow on the suction surface here. And these secondary flows, in fact, move the low momentum fluid from the shroud wall to the hub wall. And so the net effect of these changes are that by using these secondary flows, we end up moving the low momentum fluid, which was previously accumulating at the corner of the hub and suction surface. We actually move this to the middle of the passage, as you can see here inside this blue dashed line. And so the net effect of this change is that basically there is no accumulation of low momentum fluid at the end wall, and we have actually moved the positive pressure gradient forward. And as a result, the corner separation can actually be totally suppressed, as you can see from the CFD predictions here. And in fact, this is also confirmed by the oil flow visualization here that shows a complete suppression of this corner separation in the redesigned diffuser. And actually, the performance of this stage was measured, and some traverses were made both at the exit of the impeller and the exit of the diffuser in the test facility. And then what's interesting is that first of all, the impeller was made more uniform through secondary flow control. And in fact, there was a 5 points improvement in the stage efficiency. But when they actually split where the improvements were coming from, they found out that only 1/3 of the improvement was coming from impeller design. 2/3 were actually coming from the elimination of the corner separation in the diffuser. And so you can see that the diffuser can in fact play quite a major role in the performance improvements you can get from your stage.